Welcome, residents, to this Optics OCAP Masterclass. Today, we're going to completely transform rote memorization of optics into a really deep, intuitive understanding of mirrors and vergence. Now, as an ophthalmologist, you already spend a ton of time thinking about the cornea and the lens. But if you want to achieve true clinical mastery and, absolutely ace your board exams, you need to understand mirrors with that exact same level of fluency. Okay, let's dive right into this by remembering one absolutely foundational concept. Mirrors, just like lenses, manipulate the vergence of light. And because they do this, they are totally fair game for your OCAP and written board exams. Now, I see learners panic all the time when they get a mirror question, right? Because we're also used to calculating refraction through transparent media. But by the end of this explainer, you'll see that the exact same physiological and mathematical rules apply. Here is our game plan for today. We'll start with the plane mirror baseline, look at the anatomy of spherical mirrors, cover the rules of ray tracing, and then tackle high-yield board scenarios for both convex and concave mirrors. Let's kick things off with Section 1, the plane mirror baseline. This incredibly simple law of reflection is the foundation for everything we do in optics. It states that for any light ray striking a surface, the angle of incidence is identical to the angle of reflection, and this is crucial. That angle is always measured with respect to the normal, which is just an imaginary line standing perfectly perpendicular to the mirror's surface at the exact point of contact. For your written boards, you need to lock in these invariable traits of a plane mirror. Let's think through the actual physics here. A flat mirror changes the direction of light, but it never alters the vergence. Vergence in literally equals vergence out. And because of that, a plane mirror always creates an image that is virtual, meaning we have to use dashed extended rays behind the mirror to locate it, and it's always upright. Your magnification is always exactly 1.0, and your object to mirror distance perfectly equals your image to mirror distance. It's just a clean one-to-one reflection. Moving right along to Section 2, Anatomy of Spherical Mirrors. So we have two distinct flavors of spherical mirrors that actively alter vergence. Just think of your everyday silverware. We've got convex mirrors, which bulge outward like the shiny back surface of a spoon, and we have concave mirrors, which hollow inward. A super easy visual memory trick: concave curves in like a cave. Both of these are going to change the vergence of incoming light. When you're mentally mapping the anatomy of these curved mirrors, you absolutely must identify the center of curvature. Think of this center as totally analogous to the nodal point of a lens. Why is this so important clinically? Well, because every single line drawn from the center of curvature to the surface of the mirror is a radius. And since it's the radius of a sphere, it perfectly intersects that surface at a 90-degree angle. Therefore, every single line from the center of curvature acts as your normal for calculating that angle of reflection we just talked about. Now listen up, because here is a classic OCAP pearl. Burn this into your brain. R divided by 2. Unlike a lens, a spherical mirror has its primary and secondary focal points located in the exact same physical place. Because of the geometry of reflection, the focal length of a mirror is always exactly half the radius of curvature. So if they give you a radius of 50 centimeters, boom, your focal length is 25 centimeters. If you just remember that the dioptric power of a mirror is simply 1 over the focal length in meters, you can effortlessly solve any vergence equation to throw at you. Let's move into Section 3, the rules of ray tracing. There are exactly 3 rules for ray tracing spherical mirrors. Think of this like a strict surgical protocol. Step 1, a ray directed toward the center of curvature reflects straight back in the same direction. Why? Because it's hitting the mirror straight down that normal line. Step 2, a ray traveling parallel to the optical axis reflects as if originating from the focal point. And Step 3 is just the reverse of Step 2. A ray heading toward the focal point reflects parallel to the optical axis. Methodically apply these 3 steps, and you'll perfectly locate the image every single time. No guessing required. All right, Section 4. Let's apply this to a classic board scenario with a convex mirror. I want you to pause and really ponder this common board trap. Actively think through it with me. An object is located 50 centimeters from a convex mirror. The mirror has a 50-centimeter radius. Where exactly will that image form, and what's it going to look like? So, the crucial step here is plugging this straight into our universal U plus P equals V equation. Our object is sitting at 50 centimeters, so our incoming light vergence, U, is minus 2 diopters. Now, what's the power of the mirror itself?
Well, the radius is 50 centimeters, and our OCAP Pearl told us the focal length is exactly half of that, right? So 25 centimeters, or 0.25 meters. 1 divided by 0.25 is 4 diopters. But because it's a convex mirror, meaning it acts like a diverging minus lens, the power, P, is minus 4 diopters. So minus 2 diopters incoming, hitting a minus 4 diopter mirror, that yields a final exiting vergence, V, of minus 6 diopters. Because that exiting vergence is negative, the light is diverging, which tells us we have a virtual upright image. But where is it? Simple. 1 divided by 6 gives us 17 centimeters behind the mirror. And for magnification, it's just similar triangles. Image distance over object distance. 17 over 50 is about 0.33. The image is minified to 1/3 its original size. Every single time you look up at one of those security mirrors in a convenience store, this is exactly the physics happening right in front of you.
Finally, Section 5, board scenarios for concave mirrors. Try this active recall problem on for size. What happens when an object is placed 1 whole meter away from a concave mirror that has a 55 centimeter radius? Now notice here that the object is located way outside the mirror's center of curvature and its focal point. Let's run our trusty equation. The object is 1 meter away, making u minus 1 diopter. The radius is 55 centimeters, meaning the focal length is 27.5 centimeters, or 0.275 meters. 1 divided by 0.275 gives us a positive converging mirror power of plus 3.64 diopters. Minus 1 diopter incoming, plus 3.64 diopters from the mirror equals a positive exiting vergence of plus 2.64 diopters. And this brilliantly illustrates our point. Because the exiting vergence is positive, the light is actually converging to a point in real space. 1 divided by 2.64 puts the image right at 38 centimeters in front of the mirror. It's a real, inverted image. Our magnification is 0.38 divided by 1, so it is minified. Takeaway: distant objects in a concave mirror give you real, inverted, minified images. But watch how the clinical math flips entirely on its head when we move the object inside the focal point. This is a massive board favorite. Let's say the object is just 25 centimeters from a concave mirror, but the mirror has a massive 1 meter radius. Just look at the battle happening in this vergence equation. An object at 25 centimeters gives us a massively divergent u of minus 4 diopters. The mirror's radius is 1 meter, so its focal length is 0.5 meters, giving it a positive power of plus 2 diopters. Minus 4 diopters incoming, plus 2 diopters mirror power equals minus 2 diopters exiting. Because the object is inside the focal point, the mirror's converging power simply cannot overcome that massive incoming negative vergence. The light still leaves the mirror diverging. This leaves us with a virtual upright image at 50 centimeters behind the mirror. And when we do our magnification math, 50 over 25, we prove the image is magnified twice as large. Guys, this is the exact physics of a makeup mirror or a shaving mirror. You hold it close, inside the focal point specifically, to get a magnified, upright, virtual image of your face. Let's synthesize everything we've built today. I highly recommend taking a mental screenshot of this summary for your rapid-fire board review. Convex mirrors will always give you virtual, upright, minified images, regardless of distance. But with concave mirrors, you absolutely must determine if the object is outside the focal point, yielding a real, inverted image, or inside the focal point, yielding a virtual, magnified, upright image. Don't just blindly memorize this chart, though. Really understand that U plus P equals V battle that's dictating these results. As you continue your residency training and prep for your exams, I want to leave you with a clinical challenge to test your true mastery. Tomorrow morning, when you're eating breakfast, pick up a shiny spoon. Look at the back of it. Can you mentally trace the exact vergence math, the ray tracing rules, and those similar triangles to prove exactly why your reflection looks upright and minified? When you can look at the world around you and see the underlying optical equations naturally, you haven't just memorized facts for a test, you have achieved true clinical mastery. Keep up the excellent work, and I will see you in the next explainer.